Hello, welcome to a new lesson in differential equations. Today we continue with the topic of the Sturm-Liouville problem, and we want to show what is the green function associated to the Sturm-Liouville problem. We know that the green function is a tool that can be very useful to solve differential equations, and that many physical phenomena are related with a differential equation that has the form of the Sturm-Liouville problem. So we are very interested in finding what is the green function associated to the Sturm-Liouville problem. So to start, we are going to consider the Sturm-Liouville problem that is not homogeneous in the following way. We have that the derivative with respect to x of p of x, the derivative of y of x with respect to x here, plus q of x, y of x, plus lambda w of x, y of x is equal to f of x. In this case, the differential equation is defined on the closed interval a comma b. So we know that this equation that I just wrote has the structure of the Sturm-Liouville differential equation, where you should remember that p, q, w, and p prime are real continuous functions in this interval, and that w of x is known as the weight function. So we have the Sturm-Liouville problem inhomogeneous. Okay, so we are going to write this in another way to introduce the Sturm-Liouville operator. So to do that, we are going to first factor w of x. So we will have w of x that is going to multiply 1 over w of x times the derivative with respect to x of p y prime, and then plus qy of x divided by w plus lambda y equals to f of x. Okay, so as we have been working in recent lessons, we can already identify this thing as the Sturm-Liouville operator, right? So we will have here that this is w of x times the L applied to the y, and then plus lambda y equals f of x. You should remember that we defined that the Sturm-Liouville operator L is equal to 1 over w of x, that is going to multiply the derivative with respect to x of p of x, the derivative with respect to x, and then plus q of x. Okay, perfect. So again, this is the Sturm-Liouville operator. So the important thing here is that we can define the Sturm-Liouville problem inhomogeneous in this manner in terms of the Sturm-Liouville operator. So from here, the equation that we are going to need is the next. L applied to y of x plus lambda y of x is equal to f of x divided by w of x. Again, this is for an x defined on a closed interval a comma b. I mean, we can see the problem in this manner or in this manner. So we know that if we have a differential linear operator applied to a function, let's say that that operator is L, not necessarily the same as the Sturm-Liouville operator, applied to a function u of x, and this is equal to another arbitrary function f of x. For this differential equation, we can associate a green function that will satisfy the next relation. L applied to the green function is equal to the Dirac delta x minus x prime, where of course this g is a function of x and x prime. Okay, so like I mentioned, this operator that we have here is not necessarily the Sturm-Liouville operator. So from this differential equation, we can see that we have a similar structure. So if we see this L as w of x times L plus lambda, Well, this is the operator that is being applied to the y, right? Because if we multiply this by y of x, and here it is equal to f of x, well, we see that we have exactly the same expression that we have here or here, right? So we can see this as the operator L that is in this equation. Okay, so from here we can get that L plus lambda y of x is equal to f of x divided by w of x. And just for you not to get confused, this is the Sturm-Liouville operator, right? Okay, perfect. Another thing that it is important to mention is that to define the Sturm-Liouville problem, remember that there are two boundary conditions. For a solution of the differential equation, which is y, we know that alpha 1 y of a plus alpha 2 y prime of a is equal to 0, and then beta 1 y of b plus beta 2 y prime of b is equal to 0. These are the conditions that complete the definition of the Sturm-Liouville problem. Okay, and again, looking at what we mentioned, we said that we can apply an operator to a function u of x to get f of x, and this implies that we have that same operator applied to the green function that is equal to the Dirac delta. Okay, so in our case, that operator is all this thing, which is w of x times the Sturm-Liouville operator plus lambda. So we can make that process now with the green function, right? But instead of f of x, we will get the Dirac delta distribution. So we will get w of x that multiplies L plus lambda times the green function x comma x prime is going to be equal to the Dirac delta of x minus x prime. Okay, and just to see it in a more elegant way, we will have that L plus lambda applied to the green function is equal to the Dirac delta over w of x. It is also important to mention that this x prime is, of course, on the interval a comma b, like this. Perfect. You should know that for a particular green function, we will have that if it is defined on an interval a comma b, and we define the green function for it to be a function of x prime, well, we will have that when x is equal to x prime, the green function is going to be continuous, right? So the green function could be maybe more like this. It has to be continuous. But, well, actually, this turns out to be wrong because let's say maybe it will be something like this. The thing here is that the green function is continuous at x prime. But what we are going to show in this video is that the left derivative of the green function is different from the right derivative of the green function. So that means that if we take the derivative at x prime of the green function from the left, we have certain value, right, which is the slope of this graph, right? But we see that from the left, well, here it is negative, and then from the right, it is positive. So we have that the derivatives do not match. So this is just an example. It is not exactly the green function that we are going to find for the Sturm-Liouville problem, but it is to show you that the derivative from the left is not going to be equal to the derivative from the right, exactly at the point x prime. So it will be an important property of the green function, and actually we are going to show that that is true. So first of all, let me remind you that looking that we have these boundary conditions satisfied by the function y, well, the green function also has to satisfy these boundary conditions. Just remember that, well, the green function is an element of a very similar differential equation, right? But in this case, it is equal to a Dirac delta. So the thing here is that looking that the green function also satisfies this differential equation, then it also it is also going to satisfy the boundary conditions. So we can substitute the y for the green function. And we are going to get the next. It will be a constant alpha 1, which is real. Okay, remember alpha and beta are all real. And this will multiply g of, yeah, looking at while we are taking the boundary condition for a, we need to evaluate the green function at x equals a. So it will be a comma x prime, and then plus alpha 2 g prime. And let me write this as g sub x, which is going to be for the first derivative with respect to x of the green function, evaluated at x equals a, like this. Yeah, just for notation to make it, I don't know, maybe a little bit more easy to understand. And this is equal to 0. And then we will have for b that beta 1 g of b comma x prime plus beta 2 g sub x evaluated at x equals b is equal to 0. Okay, so these are like the boundary conditions that the green function needs to satisfy. So I'm going to make a quick resume on the theorem that I just mentioned for the derivative of the green function. So remember, this is always on a closed interval a comma b. So we are going to have that the partial derivative with respect to x of the green function is continuous in a comma b if x is different from x prime, okay? And this derivative is evaluated at x, okay? But if x is equal to x prime, then this derivative, well, it is not continuous. Actually, we are going to have that the derivative with respect to x evaluated at x prime from the right, and minus the derivative with respect to x of g evaluated at x prime from the left, is going to be equal to 1 divided by p of x prime. Remember that p is this function over here, okay? Perfect. So yeah, we are going to show this theorem. And to do that, we are going to start from this equation that we have here. We are going to multiply w times L plus lambda and g, and then we are going to integrate the whole equation to see what are we going to get. Let me rewrite this equation on a different page. Okay, so we start from here, and this is going to be w of x times 1 over w, the derivative with respect to x of p times the derivative with respect to x, and then plus q plus lambda that multiplies g of x comma x prime, and this is equal to the Dirac delta of x minus x prime. Perfect. So if we multiply all this thing by w, we will get that the derivative with respect to x of p, of the derivative with respect to x, plus q plus lambda w of x, all these times the green function of x comma x prime equals the Dirac delta x minus x prime. Okay, so from here we are going to get that the derivative with respect to x of p, the derivative with respect to x of g, plus qg plus lambda w g is equal to the Dirac delta. Okay, and let me point something here. We are going to take the partial derivative with respect to x of the green function because we know that it is a function of two variables. So just to express that, I'm going to consider the partial derivative with respect to x. Okay, so from this step, we are going to integrate on a neighborhood of x, which is actually going to be a variable x0, an arbitrary point of the interval a comma b, and we are going to integrate on a neighborhood of that arbitrary point. I mean that if we have the interval a comma b here, we are going to select a point x0, and we are going to see what happens on a neighborhood that is going to be from x0 to x0 plus epsilon and x0 minus epsilon, where of course epsilon has to be greater than 0. Okay, so we are going to take the integral on every element of the equation to get that this is the integral from x0 minus epsilon to x0 plus epsilon of the derivative with respect to x of p dg dx. Of course, this is a function of x comma x prime dx plus the integral from x0 minus epsilon to x0 plus epsilon of q g plus lambda w g dx equals to the integral from x0 minus epsilon to x0 plus epsilon of the Dirac delta x minus x prime dx. And I think that all this expression can remain the same, but the first element that we have can be easily solved just by watching that we have the integral with respect to x of a derivative with respect to x. So that means that we can cancel, and we will get p times the derivative of g, which is a function of x comma x prime, like this, and it is evaluated from x0 minus epsilon to x0 plus epsilon, like this. Perfect. So how are we going to analyze this expression? Well, remember that we are interested in showing that the derivative from the right and from the left are different evaluated at x prime. Okay, so we need to see what happens when x prime is equal to x0 and then different from x0. Okay, and notice that the integrand of this integral, well, it only includes continuous functions. Remember that we mentioned that the green function is continuous at every point on the interval. So to be able to evaluate the value of the derivative, we know that we need to take epsilon to be equal to 0, or actually to approach to 0, right? Just to be close to that value x0 that we are interested in. Okay, so looking that we have a well-behaved function here in the integrand, and we take the epsilon to be close to 0, we will be integrating a function on an interval that goes from x0 to x0. So it is easy to see that, well, that thing is going to be equal to 0. Okay, so we are going to start first by saying that what happens when x0 is different from x prime? Well, if we take epsilon to be close to 0, again, this integral is going to be 0. And for this element, we are going to have p of x0 that is going to multiply the derivative of g evaluated at x0 with respect to x. But looking that we are in the upper limit of the integration, this comes to x0 from the left, right? Because we come from the value x0 plus epsilon. So we are approaching x0 from the right. Sorry, I think I said the left. We are getting to close. We are getting to x0 from the right. So let me put a plus sign to express that here. And then for the fundamental theorem of calculus, we will have the derivative with respect to x of g evaluated at x0 from the left, and then x prime here, right? Okay, perfect. So this can be equal to the limit as epsilon goes to 0 of the integral from x0 minus epsilon to x0 plus epsilon of the Dirac delta, like this. So we know that x prime is not equal to x0. So as we approach to x0, making epsilon to be close to 0, we know that that x prime is not going to be x0, and it's not actually going to be in the interval x0 minus epsilon, x0 plus epsilon. So we know x prime is not equal to x0. So as epsilon goes to 0, x prime is going to be out of the interval of integration. Okay? So that is the main idea, because that is going to make this integral to be equal to 0. Because we know that if we have the integral of the Dirac delta of the variable x, and x is not on the interval of integration, that integral of the Dirac delta is equal to 0. So in this case, we are showing that x prime is not going to be part of the interval of integration. So that means that all this piece is going to be equal to 0, right? Okay. So if this is equal to 0, we are going to get that the derivative of g evaluated at x0 that approaches from the right is equal to the derivative of g with respect to x evaluated at x0 from the left, like this. So this is if x0 is different from x prime, okay? So that means that if we have the interval a comma b, here is x prime and here is x0, well, we know that the derivative of the green function is going to be continuous, right? Because the derivative from the right matches with the derivative from the left. Okay, perfect. So again, this is just when x0 is different from x prime. Right now, we are going to show that when x prime is equal to x0, actually these two things do not match. Okay? Okay, but first, just let me mention again. What this is telling us is that actually the derivative with respect to x of g is continuous on a comma b only if x0 is different from x prime. Okay, perfect. So now we are going to jump into the case when x0 is equal to x prime. And let me bring back the integral that we had above. Okay, perfect. We had found out that, we have this thing over here that we need to evaluate. Then this integral that is also going to be equal to 0 because this is an integral of x. So if x0 is equal to x prime, this doesn't change anything in this integral. So here is the interesting thing. If x0 is equal to x prime, doesn't matter if epsilon tends to 0. This is x0 equal to x prime, and this is our epsilon, right? x0 plus epsilon. It doesn't matter if epsilon goes to 0, making this interval to be shorter and shorter. Looking that x0 is equal to x prime, x prime is always going to be inside that interval, doesn't matter how small it is. So that thing means that we are going to be taking an integral on an interval that contains this x prime that we have here in the Dirac delta. So we know that when we have the integral of the Dirac delta on an interval that contains the variable that is inside the Dirac delta, well, that integral is equal to 1, right? Okay, so this thing is going to be 1. Perfect. And from here, we have again the same thing. We evaluate at x0 because epsilon tends to 0. And we have p of x0 that multiplies. And let me write this in this notation. It will be g sub x, x0 from the right. Sorry, x0 from the right, x prime, minus gx evaluated at x0 from the left, x prime, equals to 1. So this is immediately telling us that the derivatives from the right and from the left are not equal. So we know that when the derivative, well, in this case, the function, which is the derivative, is not equal from the left and from the right, well, that function cannot be continuous. Okay? Perfect. But we can still get an important result from here that is going to be the derivative of g with respect to x evaluated at x0 from the right minus the derivative of g with respect to x evaluated at x0 from the left is equal to 1 divided by p of x0, which is, remember, p of x prime. Okay, perfect. With this, we have shown what we wanted. But we still need to continue a little bit to find out what is exactly the green function associated to the Sturm-Liouville problem. We know that from these results that it will be convenient to separate the problem on two pieces, one from a to x prime and then from x prime to b. Okay, so we are going to express that the green function is going to be, well, a function defined by parts, which is going to be, for the first part, g1 evaluated at x comma x prime, and this is if x is less than or equal to x prime, and then g2 of x comma x prime if x is bigger than or equal to x prime. Remember that we know that the green function is continuous at x prime, so actually these two functions are going to be equal at x prime. So that's why I wrote less than or equal to x prime, right? Well, because these two functions are going to be equal at that point. Okay, so if we go back a little bit, just to remind you an important result that we had before, this one over here. From this, we can see that if we locate under the value x prime or above the value x prime, we can take this expression to be equal to 0, right? So that is because we are not considering x prime, right? So that means if x is less than x prime, we are going to have that L plus lambda times g1, which is the function defined under x prime, should be equal to 0, right? Again, we do not write the Dirac delta because we are not in the value x prime. And then if x is greater than x prime, then L plus lambda times g2 of x comma x prime should be also equal to 0. Okay. Perfect. And now we are going to consider that g1 of x comma x prime can be seen as a function, let's say c1 of x prime, of another function y1 of x, and then g2 we are going to think it as a function similar, that is c2 of x prime times y2 of x. So what we are doing here is to split the green function into two pieces and to express it as the product of two functions, that the first one is of x prime and the other one of x, looking that we know that the green function has to be a function of two variables. Okay, so we are going to write it in this way. G of x comma x prime is equal to c1 of x prime y1 of x if x is less than x prime, and c2 of x prime y2 of x if x is greater than x prime. Perfect. And noticing that these y1 and y2 come from these two equations that we have here that are, well, are very, very similar to the Sturm-Liouville homogeneous differential equation. Remember that that equation is of the form L u of x equals minus lambda u of x. Okay? So we see here that the green function 1 and the green function number 2, well, they satisfy this structure. That means that these pieces, y1 and y2, are also going to satisfy the boundary conditions of the Sturm-Liouville problem. Actually, looking at y2 of x is defined for x above x prime. y2 of x is the function that is going to satisfy the boundary condition for the b value, right? Because b is going to be above x prime, but a is going to be under x prime. So the function that is going to satisfy the boundary condition for a is going to be y1 of x. Okay, perfect. So here we are going to use the results that we found for the green function and the derivative of the green function. We know that at the value x prime, the green function needs to be continuous. So that means that we can evaluate the green function g1 at x prime, and it should be equal to the green function number 2 evaluated at x prime. Okay? So that means that g1 evaluated at x prime comma x prime should be equal to g2 of x prime comma x prime. And notice that, well, g1 is this function over here and g2 is this function over here. So it is easy to see that then this implies that c1 of x prime, y1 of x prime minus c2 of x prime, y2 of x prime is equal to 0. So I think that this is an important equation to remark. And then we are going to use the second result that we found, that the derivative with respect to x of g1 minus the derivative with respect to x of g2 should be equal to 1 divided by p. This thing over here. In this case, this element is going to be for the derivative of g2 with respect to x, because we are approaching from the right. So when we approach to x prime from the right, we are in the g2 region. And when we approach from the left, we are in the g1 region. Okay, so we will have the derivative of g2 minus the derivative of g1 equals to 1 divided by p of x prime. Okay, so we are going to write this here. So we have the derivative of g2 with respect to x minus the derivative of g1 with respect to x is equal to 1 divided by p of x prime. Okay, but we know what is the shape of g2 and g1. This is g1, so this is g2, and we will have that c2 of x prime, y2 of x prime, and the derivative, right? So recall that we are taking the derivative with respect to x of g2, but with respect to x, well, we only have one function. In this case, c2 will be considered a constant because it's not a function of x. So we will have c2 of x prime times the derivative of y2 with respect to x evaluated at x prime. That's important. So it will be something like this. And then minus c1 of x prime, the derivative of y1, well, let me write it in the same notation. y1 prime evaluated at x prime equals to 1 divided by p of x prime. Okay, so from here we can construct the next system of equations. It will be c1 of x prime, y1 of x prime, minus c2 of x prime, y2 of x prime equal to 0, and then minus c1 of x prime, y1 prime of x prime plus c2 of x prime, y2 prime of x prime equals 1 divided by p of x prime. Recall that we are interested in finding c1 and c2 because are the functions that we still don't know to define g1 and g2 and then to construct the green function, which is our objective. Okay, so we are going to use the Kramer method to solve this system of equations. So how are we going to do it? Well, this will be c1 of x prime should be equal to a determinant, right? Here we are going to put 0 and then 1 divided by p. And then here we will have minus y2 of x prime and then y2 prime of x prime. And then this is divided by, well, the determinant of the coefficients. So that will be y1 of x prime. It will be minus y2 of x prime, y1 prime of x prime, and then y2 prime of x prime. And I think that there is a minus sign here. Recall that whenever you calculate a determinant, you can take out a common factor minus 1 in this case. For example, if we take this minus sign out of the determinant, we can just multiply the whole determinant for that element, right? So this will be something like minus 1 times y1 minus y2 and then y1 prime and then minus y2 prime. And then from here we will be able to take this minus out again of the determinant. So it will be minus 1 squared times y1, y2, y1 prime, and y2 prime. Okay, just by tricks on calculating determinants, well, all these things is going to be minus y2 of x prime times 1 divided by p, all divided by, well, this determinant that we have here. But you should know from your basic course in differential equations that this matrix is known as the Wronskian of y1 and y2. And I think that I should put plus here, right? Because we have minus this thing times this thing. So minus times this minus is going to be a plus. Okay, perfect. So with this, we have found that c1 of x prime is equal to y2 of x prime divided by p times the Wronskian evaluated at y1, y2. Okay, let me remark this result. And we are going to start to calculate c2 of x prime. So c2 of x prime is going to be y1 of x prime minus y1 prime of x prime, and then 0, 1 divided by p, and divided by, well, this determinant, which we know that is the Wronskian evaluated at y1 and y2. So from here, we are going to have that y1 of x prime times 1 divided by p divided by w. And with this, we can see that c2 of x prime is equal to y1 of x prime divided by p times w. Okay, perfect. So from here, now we are able to construct the whole green function. Remember that we defined that green function is of this form. Okay, so g of x comma x prime is equal to c1 of x prime, but that is y2 of x prime times y1 of x, all divided by p of x times w of y1 comma y2 if x is less than x prime. Yeah, let me put some order here. And then the second piece will be c2 of x prime, which is y1 of x prime divided by p of x, w of y1 comma y2, and then this multiplies y2 of x. And this is if x is greater than x prime. Recall that the green function is a function of two variables. So we have dependence on x prime and x on both pieces that we wrote. Okay, and actually, I should say that this interval is actually for a less than or equal to x, which is less than x prime, less than or equal to b. And this is for x, which is greater than x prime, but less than or equal to b, and x prime is greater than or equal to a. Okay, perfect. So with this, we have shown what is the green function associated to the Sturm-Liouville problem. It will be defined in this huge way. Okay, so I think that with this, I'm going to finish the lesson, and I hope you enjoyed it. Thank you so much for watching.